So today we have a new chapter. We have chapter 4. So this chapter entitled Entropy. So basically in previous chapter 3, we talked about the first law of thermodynamics. So we started with conservation of mass. Then we explained the conservation of energy, which is the first law of thermodynamics. In this chapter, we will start, or we'll talk about the second law of thermodynamics. The second law of thermodynamics, this is called law of entropy. This is why we need to talk more about entropy. What is meant by entropy, how we can calculate it. But in order to understand the second law of thermodynamics, we need to understand some basic concepts. So we need to understand what is meant by reservoir, what is meant by reversibility, and then heat engines and thermal efficiency. So these 4 concepts, we need to understand each one of them. Because when we understand all of them, then you can understand the statements of the second law of thermodynamics. You can understand the application of the second law of thermodynamics. After we understand these concepts, then we will explain what is meant by entropy, where it comes from, and start with the universal statement of the second law of thermodynamics. Then we will show the entropy balance and some examples. Okay. So this chapter we need to understand the second law of thermodynamics and how we can use it with the first law of thermodynamics to analyze like ideal equipment or actual equipment that we can see in different chemical processes or environmental systems. Okay. So if we start with the second law of thermodynamics, so let's recall what we have in previous chapters. So previous chapter we talked about conservation of mass. Again, previous chapter we talked about first law of thermodynamics, conservation of energy. These laws are principles in any like engineering application. The conservation of energy, this one if you remember, it focuses on how the form of energy or how the energy can change from one form to another one, right? So this is like one of the common themes that you can see in all engineering applications. If we focus on the first law of thermodynamics or conservation of energy, so this one says it's possible that we convert any energy from any form to another one. So this is the general statement of the second law, first law of thermodynamics. So the generalized energy balance, as we said, it's one of the fundamental tools we have to model like any chemical, environmental, or in general engineering applications. The thing is, the energy balance, it doesn't have, or it says that it's possible to convert energy from one form into another one without any restrictions, without any limitations. So the first law of thermodynamics, again, it says energy is conserved property. You can convert energy from one form to another one. There is no limitation, there is no restrictions. Clear? However, this is not true. We have limitations and we have some restrictions in this. Let's take this example. So if we have hot coffee, for example, and you put this hot coffee on the table, so what will happen to the temperature of this coffee over time? The temperature will decrease, right? This is the first law of thermodynamics. We have heat loss happen to the system. But if you have hot coffee and you put it in the table, first law of thermodynamics says it's possible that its temperature will increase. Okay. Because again, we have energy is converted from one form to another one. So there is no, so this one, or what I'm saying right now, just if you put hot coffee and its temperature will increase over time, if you just put it, this is not violating the first law of thermodynamics. Okay, this is fine with the first law of thermodynamics. But for you, it doesn't make sense. This will not happen. And this is the issue that we have with the first law of thermodynamics. First law of thermodynamics doesn't put any limitations or any restrictions on the energy transfer. One of the other things, do you remember the dynamic forms of energy? Heat and work, right? That the forms of energy that can cross the boundary between system and surrounding. If you have like water inside the tank and you have a shaft, and this shaft starts to rotate. So over time, what will happen to the temperature of this water? It will increase because heat, work is converted into heat. But if we opposite the process, if we have water and we have like a heater in order to increase the temperature of this water, so do you think the shaft will rotate by itself? No. So the heat cannot be converted like automatically into work. Again, first law of thermodynamics says this is possible. Any of these 2 observations are possible. If you have work, this work can be converted into heat. If you have heat, this heat can be converted into work without restrictions, without limitations. Okay? So this is one of the like not shortcoming, but this is like incomplete like picture of what first law of thermodynamics is describing. So the problem is, first law of thermodynamics doesn't have limitations or restrictions on the energy transfer or the energy conversion from one form to another one. But in reality we have like process can occur in a certain direction. Okay, so or to overcome this like incompleteness in the first law of thermodynamics, we need another law, which is the second law of thermodynamics. So again, the first law of thermodynamics, this one is not sufficient in order to describe how the process will behave. So this is why we need second law of thermodynamics. Second law of thermodynamics, this one said that any process to occur, it should fulfill both laws, first and second law of thermodynamics. So this is why if we return back to this example, we said this one will occur because this one fulfilled the first law of thermodynamics, the second law of thermodynamics. So this is why spontaneously it occurred. But this one will not occur. It fulfilled the first law of thermodynamics, but it has some limitations, or it doesn't fulfill, or it violates the second law of thermodynamics. So this is why spontaneously this process cannot occur. So any process you have, for this process to occur in a spontaneous way, without any external force, so it should fulfill these two laws. First law of thermodynamics, that related to the energy transfer, and the second law of thermodynamics, the one that's related to the entropy. So far is clear? Okay. So this is the second law of thermodynamics and why it's important and how it overcomes the insufficiency we have in the first law of thermodynamics. We have other applications or uses for the second law of thermodynamics. So it identifies the direction of the process. It will help you with the first law to tell you the process will happen in this direction, not in that direction. Okay, so the direction of this process. Also, it determines the theoretical limit of your process. So if you have any equipment and you need to like assess the performance of this equipment, the efficiency of this equipment, so the second law of thermodynamics help you to know what is the maximum performance you can obtain from this process. So this one, it determines the theoretical limit. Theoretical limit, this one means the maximum efficiency that you can have from this process. Okay, and as we said, this law, or the second law of thermodynamics, this law is called the entropy law because it's all based on the entropy we have. Okay. So far, clear? Any questions? Okay. So now, if we just Google the statements of the second law of thermodynamics, when we describe the first law of thermodynamics, we had only one statement describe the first law of thermodynamics. That energy cannot be created nor destroyed, can be changed from one form to another one. Again, this law doesn't state any restrictions, any limitations. But the second law of thermodynamics, if you Google it, the second law of thermodynamics, you can find hundreds of statements that describe the second law of thermodynamics. Okay. The most common statements we have from the second law of thermodynamics are these three. We have Kelvin-Planck statement, we have Clausius statement, and recently we have the universal statement, which we are using right now. The Kelvin-Planck statement, it says the second law of thermodynamics, according to their experiments, it says it's impossible for any device that operates in a cycle. Do you remember the cycle? If the initial and final conditions are the same or different? Are same. We have cycle, so we return to the same initial condition. If you have any device operates in a cycle to receive heat from a single reservoir, it's impossible for any device operates from a cycle to receive heat from a single reservoir and produce a net amount of work. So this is the statement of the second law according to the experiment that Kelvin and Planck did. Clausius, he did other experiments, and according to his experiments, he listed his observations in a statement described the second law of thermodynamics and says it's impossible to construct a device that operates in a cycle, produce no effort other than the transfer of heat from low temperature body to a higher temperature body. We have other statements, and at the end we have a universal statement. It says any process to take place spontaneously without any external assistance, the total entropy change is more than or equal to zero. And here we have a limiting case that if a process operates in a reversible way, this entropy change will be zero. So what we need to know from this slide again. So first law of thermodynamics, we have one universal statement for it. Second law of thermodynamics, we have hundreds of statements. So why we have hundreds of statements? Because each scientist or group of scientists, they did some experiments. And according to their experiment results and their observations, they put a statement that described the second law of thermodynamics. There was no connection between all of these experiments until we have this universal statement, until we have the description of entropy. So once we understand what is meant by entropy, so we can combine the hundreds of statements into a single universal statement. So this universal statement here gave the same meaning of this one, Clausius statement, gave the same meaning of Kelvin-Planck statement. So far it's clear? If I am a student and someone gave me this slide and tell me, do you understand anything? For me, I didn't understand anything. Okay. These statements, I can understand what I'm saying right now, that we have hundreds of statements based on the experimental results that these scientists have, and all of these statements are combined or integrated together in the universal statement. But the question, what this mean? What is mean by if you have cyclic process in order to, it's impossible to receive heat from a single reservoir, or it's impossible to have heat transfer from lower temperature body to higher temperature body. In order to understand these statements, which I'm not expecting you to understand these statements right now, in order to understand these statements, we need to understand four main concepts. When you understand these four main concepts, then we can recall the statements and you can understand what Clausius means, what Kelvin-Planck means by his statement, even what is the universal statement like means. Okay. So these four statements, we have heat reservoir, we have reversibility, heat engines, thermal efficiency. Heat engines, this is your part that you are asking about. So heat reservoirs, if we need to understand it, the first one that we will see a lot starting from this chapter. Heat reservoir, this can be a heat source or can be a heat sink. So any heat reservoir, it can be classified into source of heat or sink of heat. It will be called source of heat if it's applied energy. It will called sink if it absorbs energy. And the main feature of this reservoir, it can absorb heat or it can supply heat without significant changes in its temperature. So if you have huge system and this system gain amount of heat, or this system like lose amount of heat and its temperature is not like changing, or you cannot observe significant changes, so this can be considered a reservoir. So again, you have large system, this system is considered source if it gives heat to the surrounding. Or this reservoir is called sink if it's absorbing heat from the surrounding. And again, the key is no significant changes in the temperature can happen. So let's see examples for this one. Large bodies of water like oceans, lakes, rivers, all of these. This is huge amount of water. The changes in temperature of these large bodies will not be significant. So when we have any system like, and we have analyzing all of these things, all of these large bodies, this can be considered a reservoir. If we have two-phase system, like phase change process. Two-phase system, if you remember from chapter 2, we have phase change for pure substance happen at constant temperature, at constant pressure, right? It can absorb heat or it can gain heat. This heat is called latent heat. This latent heat doesn't cause temperature changes. So these two-phase systems is as a temperature of reservoir. You can add heat, remove heat during the phase change process without temperature change. If you have industrial furnace, these ones are like controlled in order to maintain the temperature at constant temperature. So it gives a huge amount of heat, but at the same time we have control system to maintain the temperature at constant. So this is also considered a reservoir. So any system gives heat or absorbs heat without observing significant change in its temperature, this is called what? A reservoir. So far as clear? Clear? Awesome. So this is the first part, or the first concept we need to understand. The second concept is reversibility. So what does mean by reversibility? Reversibility means we have a reversible process. This is a process that can be reversed without leaving any trace on the surrounding. So what this means, do we have system and we have surrounding, right? So you have changes happen to the system. Let's assume you have initial condition for the system and you change this initial condition to a second condition. This is a process. Now, if I ask you to return it back from the second condition to the initial one, and you did it, I return it from the second condition to the first or the initial condition. Okay, so we have changes happen to the system, but you return it back to the same as initial condition. If the surrounding itself, like have any changes happen, this is not a reversible process. If there is no changes you can observe in the surrounding, then this is called a reversible process. So again, you have system, you have surrounding, they are affected or influencing each other. For the system, we have some changes happen to the system, but you return it to the initial condition. For the surrounding, if you have any changes happen to the surrounding through this process, this is irreversible process. But if the system returned to the initial condition and at the same time you cannot observe any changes happen to the surrounding, so the surrounding itself returned to the same as its initial condition, or its surrounding not affected by the changes happen to the system, this is the example of a reversible process. So far is clear? So reversible process means the system returned to the initial condition, the surrounding not affected with the changes happen to the system. Okay? So reversible process, one of the comments, actually does not occur in nature. There is nothing in nature called reversible process. You cannot achieve reversible process in nature. But the thing is, we can approximate some of our processes. If we have any actual device, you can operate this device in a way that try to approximate the reversible performance, but you can't achieve it. Okay? Reversible process, this is an ideal operation of a process, something ideal. Okay, you can't achieve in nature, you can't achieve in actual devices, but we are trying to like approximating the performance approximating the performance of these actual devices to be similar to the performance of a reversible process. But in theoretically, you cannot exactly achieve the reversible performance. Okay, as we said, any process that is not reversible, it's called irreversible process we have here. So if this reversible process, something like does not exist in nature, okay, something ideal, we don't have any actual equipment operating this one. So why it's important to understand reversibility? Or why even we use this reversible assumption in our analysis? The thing is, we have some characteristics in this reversible process. These characteristics will give you some advantage in the analysis. So if we start with the characteristics, all the driving force for the change in the reversible process are very small. So if you have heat transfer, what is the driving force for heat transfer? Temperature difference. If the temperature difference is very small, then we can say we have a reversible process. What is the driving force for mass transfer? Concentration difference. If the concentration difference is very small, then the mass transfer we can approximate or assume it behaves as a reversible process. The process itself, it occurs or progresses through a series of equilibrium states. So the process itself happens through several states or several steps. These steps can be described as equilibrium states. It takes long time. So this one, it implies that the time needed for this process to occur, it's very long time. And one thing we have, this can be returned to the original state with no net addition of heat and work. So as we described, the system returned to the initial state, the surrounding not affected by this one. There is no net heat added or removed or work added or removed between the system and surrounding. And also we have no friction happening. So this means we have no losses happening in this way. So these are the main characteristics of reversible process. So again, let's summarize it. We have something called reversible process. This is an ideal process, just a theoretical description of the performance of the process if we have these four main characteristics. Okay. But in actual, there is no reversible process. All the process we have in actual are irreversible. But if you operate any process, you just try to approximate the performance as the way it will operate in a reversible way. Okay, so far is clear? Okay. Let's take an example to see the difference between irreversible and reversible process. If I give you this piston, and I have this piston at this position, and then you put a weight, let's say you get a 1,000 kilogram inside of this piston. So what will happen to the piston? The piston level will go down, right? So what will happen to the volume inside the piston? It will decrease. So we have this example compression process. If you plot prefer the plot. If we need to approach the same like outcome we have from this process, but instead of put 1,000 kilogram just one time, we will put two weights. Each one is 510 kilogram, which will give you the same total as this one. So you need to make compression, but one experiment, what you did, you have a big mass. Its mass is almost 1,000 kilogram, and you put it in the piston to have the compression. Or you have two masses, each one is almost 500 kilogram. So you put the first one first, and then after some time you put the second one. Or if you have a very small balls, and the weight of all of these balls is the same as 120 kilogram. But you have hundreds of these balls, the weight or mass of each ball is very small, and you put it just one by one. Okay? So at the end, you will have the same compression achieved, right? But what's the difference between them? Here you have just one step. In the first one, you make the compression on one step. You put this huge mass, and then you have sudden compression happening. Here in the middle, you have two-step compression. You put the first weight, you have compression to the middle, for example, then you put the second weight, then you will have compression to the end. Here in this case, you have very slow compression happening. You put one ball. So even you cannot observe the movement in the piston. Then you put the second ball. So the movement is very small. The third ball. So the piston is moving very slowly. The process takes a lot of time in order to finish all the balls we have, and you finish the compression process that you need. If we compare the amount of work that you can obtain from this process, so the amount of work, if we put like, if you remember the PV diagram, pressure, molar volume diagram, let's assume this is the first condition we have, this is the second condition. For the first case, if we put the one mass we have, so we'll have the compression happening in this way. And again, what is the work? Area under the curve. So this area, this gray area will represent the amount of work you can obtain from this process. Make sense? For the second step we have, again, this is the initial condition, same as we have here. This is the final condition, same as we have here, but the way we moving from 1 to 2 will be different. So here we put the first 500s, so we'll have compression up to here. This is intermediate because I put the first one, M1, which is 510 kilogram. Once I achieve this compression level, I add the second mass, which is also 510 kilogram. So then I will have the second compression. Area under the curve, the gray area here, this representing the work. So according to this one, if you remember, work is a path property, multi-state function. Path property means it depends on the way you have or you are operating the process. So if you compare this one, first one and this one, which one will give you more work? Second one. So when you like split the process into steps, then you can obtain more work. Even if you have the same initial condition, you have the final condition, but the path, the process path we have affecting the amount of work you are obtaining. So if you have it like very small balls, like this one, so if we apply the same approach, here we have just one step of compression, two steps of compression, here we have several steps of compression. So what we're expecting and the amount of work here will increase. So if we have it, this is the initial condition, this is the final condition, here the steps will be very slow, and you can approximate it as this curved line, and this will be the area under the curve. Okay, so here this is one example that gives you an idea about how you can operate your process can affect the output you have of your process. So for this compression, I'm obtaining work. The amount of work here in this pass is small. I can increase the amount of work if I change like the weights I'm adding. And here, if I have like hundreds of these tiny balls, I can obtain the maximum amount of work I can have. So there is a way that gives you the maximum amount of work. But if you are like working in a plant and you need to like have the changes happen to this process, with this one will give you the maximum work, okay? But in terms of time, this one needs more time or less time?
More time.
This one needs more time, okay? So this one gives you maximum work, but the amount of time needed to achieve this amount of work is huge. It's very long time, and no one was waiting in industry for this time. So this one, in industry, they can use this like approximate, for example, to compromise the minimum amount of work they can obtain from here and compromise the significant or prolonged time that they need to have this maximum amount of work. So this is why reversible process, it's like doesn't exist in actual, because no one is waiting for this prolonged time in order to like just to get the maximum work we have from this process. So far is clear? Okay. So if we need to compare this, this is an example of a reversible process. But all of these are irreversible. Because this process happens very quickly. The amount of work we obtain from this process are less than the amount of work we can obtain from this one. If we operate our process in this mode, so we can obtain the maximum amount of work, but it will take a long time. The changes that happen are very small, so the surrounding will not be affected by any changing happen to the system. Because when you put one ball, the changes you have will be very small. The surrounding will not be affected by it. Wait for some time, add the second one, then add the third one, and continue adding these balls until you have the final compression level. So far is clear? Okay. One of the other things that can explain why this is reversible and these two are irreversible is how the surrounding is influenced by the system changes. And let's show it in this example. Here we have the isothermal process. Let's say this isothermal compression, I put this weight, okay? And then we have expansion. I remove this weight. So I have here some condition, I make compression, then I make expansion, okay? So I reverse the same process, so I don't have any changes happen to the system, right? I compress the system, then I expand the system. So overall, no changes happen to the system. Make sense? Okay. If we plot the PV diagrams, so the PV diagrams for this one, initial state, the final state, this is the amount of work like I obtained during the compression. Then for the expansion, I return from the second to the first. All the area under the curve represent the amount of work during the expansion. Do you think the first gray area here is equal to this gray area, or they are different? So we have two work values. One we have during the expansion, one we have during the compression. They are not equal, so we have difference in work here, and this difference, all of this difference will go to the surrounding. So the surrounding will be affected because we have some energy difference between the first process compression, second process expansion. We have some difference in the energy. This energy will influence the surrounding. So you can observe changes happen to the surrounding. So this is why this is irreversible process. So it happens very short. It takes less amount of time. The amount of work obtained from this process, expansion and compression, are not the maximum compared to the reversible one. And at the same time, if you reverse the process, if you have expansion and then compression for the system will return to the initial condition, but we have net amount of energy. This net amount of energy will have or cause some changes to the surrounding. Clear? Okay. But if we have like this process we here, if we add this ball, you continue adding the balls to make compression, so we'll have this path from 1 to 2. If you have the expansion, remove one by one. So what will happen to the path? It will have the same path during the expansion. So the same amount of work you obtain during the expansion and during compression. So the network is what? 0. We don't have network here. So here for this one, the network or net energy This one is 0. When I say the net work or the net energy, this one is the energy during the expansion minus energy during the compression. So for this process, very slow process, I keep adding one by one. So the same amount of energy I obtained during the expansion, same amount of energy I obtained during compression. So the network is 0, so the surrounding will not be affected. Because the process, it's very slow. The driving force, the size of the bolts is very slow, so the driving force is very small, so the surrounding is not affected by this one. So in summary, we have this one. If we have a process happening in this way, this is an example of irreversible process. The amount of work is not the maximum. The surrounding will be affected by the changes happening to the system, even if the system returned to the initial condition. But here for this one, the operation or the way that we are performing this compression in this way is an example of reversible process. The system will return to the initial condition. The amount of work you can obtain from the system, this is the maximum. The surrounding will not be affected. No changes will happen to the surrounding. So this one we have the 4 features can like fulfilled in this one, not in this one. Clear? Any questions? Sure.
So if you have like a million infinitely small steps, then would it be fully reversible?
Yeah. So it's if you increase the number of steps, then you are decreasing the driving force, you are increasing the time, you are cancelling any effect that will happen to the surrounding, and then you are obtaining the maximum output of this process. Just what you said, you have these 5 things will happen. So this will be a reversible process. Any questions? Okay. Let's take example. This is an example of irreversible expansion. This example says we have 2 moles of an ideal gas are confined in a piston cylinder device. These 2 moles initially at 0.5 megapascal, 300 Kelvin. The surrounding is also at 300 Kelvin, and the atmosphere is 0.1 megapascal. So, but clamps hold the piston in a place as shown in this figure. When the clamps are removed, so we remove a clamp from this one, the gas expands rapidly. When you hear these words, if I didn't say this example is for irreversible process, but you see this word, we have like a rapid expansion. So this, in this word tells you the process is reversible or irreversible. Irreversible, because we have rapid expansion. Rapid means the time for this process is small, and this is not the feature of reversible. The reversible process takes very long times. Okay? So we have rapid expansion happening. So rapidly the heat transfer is negligible during the step until the pressure of the gas is 0.1 megapascal. Heat is then transferred to the gas from the surrounding until it reaches its final state, 0.1 megapascal, 300 Kelvin, which is the final state of the gas here. Find the total work done by the gas on the surrounding and the total heat transfer to the gas. So we need to calculate W, we need to calculate Q in this example. So in order to analyze this one, so this is the picture of the system we have here, then we need to have the calculate work, calculate W, and in order to calculate work, calculate W, we have the first law of thermodynamics. So in this one, we need to apply first law of thermodynamics, which is energy balance equation. So energy balance equation, general one is accumulation, is inlet or initial condition minus final condition or outlets plus work of expansion contraction plus shaft work plus Q. So for this example here, we don't have all of these terms. So this initial or energy balance equation will end up with the work of expansion contraction. This is negative Q. And this is what we need to calculate. So in this example, we need to calculate the work and we need to calculate the Q. So how we can find work of expansion contraction? So if you remember the equation of this one from chapter 1, work of expansion contraction is negative integration of P dV. This is from initial volume to final volume. Okay. For the work of expansion and contraction, the pressure we have here, this one is the external pressure. And the external pressure we have here, initially it was 0.1 megapascal, and finally it remains 0.1 megapascal. So the pressure is constant during the process. So in this example, we have pressure is constant. And this pressure is 0.1 megapascal. Since it's constant, I can take it out of the integration term. So I can say work of expansion contraction, this one will be negative P V2 minus V1. Okay. I know the pressure I have, the value of this pressure. (0.1 megapascal). Megapascal, this is not SI system. Pascal, this is the units in the SI system. So this one will be 0.1 times 10 to the power 6 Pascal. Then I don't know the initial volume. I don't know the final volume. I know that from his example he says it's an ideal gas. So since we have ideal gas, so we have PV equal nRT. So this implied that V is nRT over P. And for the initial condition, we have number of moles, we have pressure, we have temperature, same for the number of moles. So we can substitute in this one here. So we have initial conditions, we have number of moles is 2 moles. We have pressure is 0.5 times 10 to the power 6 Pascal. We have temperature is 300 Kelvin. We have R, the ideal gas constants. Here I will take the one in the SI system, 8.314 joule per mole Kelvin. So substitute in the equation, and then you will have V1 will be 0.01 meter cube. Repeat the same calculation for the final conditions. We have the same R value, still have number of moles, 2 moles. We have final pressure, 4.1 times 10 to the power 6 Pascal. We have final temperature, 300 Kelvin. Then the final volume we have is 0.05 meter cube. So we have V1, we have V2, we have the pressure is given, then we can say that according to the numbers we have, the work of expansion contraction we have will be negative 3990 joule, and substitute in the energy balance equation, then the amount of heat will be 3990 joule, and this is what we need to calculate. clear? Any questions? Okay.
There is a change in pressure, so like
Where?
from 0.5 to 0.1.
Okay.
Wouldn't that mean you set E equal to N R T over V and then integrate?
You mean here or here?
Or like, I don't know.
Okay. So here, okay.
You said pressure was constant, but it's changing like in the liquid, I guess,
No.
or the gas.
Which pressure is constant? The external pressure.
Okay.
Okay, the external pressure is 0.1 megapascal initially, and finally it's also 0.1 megapascal. The pressure of the gas is changing from 0.5 to 0.1. So this pressure change is represented in the initial and final conditions in volume calculations. But the outside pressure, this is the external pressure we are using in the expansion contraction work. Okay. Okay. Another example, same process we have, but this one we have reversible expansion. So again, we have ideal gas, 2 moles of this ideal gas at the same pressure, 0.5, 300 Kelvin. But this time, instead of having this clamp we remove, we have sand. And then we are removing this sand one by one. So now, this description tells you the process will take very long time because we have sand on the piston and we are removing like this sand. Okay, so this will be an example of a reversible process. So what is happening here? The pressure at the end of remove all the sand will change from 0.5 to 0.1 to this temperature. Again, calculate the work of expansion, contraction, calculate the heat. So almost this is exactly the same example. Instead of we just have like a lock and you remove the lock, so we have rapid expansion. So this one we have sand, and then you are removing this sand and expansion is happening very slowly. Okay, so this is like an example of a reversible process to see how the calculations will change. So for this process, again, as we said from previous example, we have work of expansion contraction. This will be negative Q. And then we need to calculate of work of expansion contraction. So we'll have the same equation. Work of expansion contraction is negative integration of P dV from V1 to V2. In the previous example, we said we have the external pressure. The external pressure will not change because we have like sudden expansion happening. But here what we have this process is very slow. So this pressure, which is still pressure of the surrounding, external pressure, if you remember the main characteristics of reversible process, we have the process happen on several steps, and these steps are described as equilibrium steps. So this means the surrounding and the system will be at equilibrium. So since here we have reversible process, so this means the changes will occur through via equilibrium stages. So this means the external pressure and the internal pressure are in equilibrium. So this one here, this external pressure, so the pressure of the surrounding can be approximated or in equilibrium with pressure of the gas inside the piston. And the pressure of the gas in the piston is 0.5, becomes 0.1, is not constant. So here in this case, the pressure is not constant. Is this one clear? So we can't take the pressure out of the integration in this case. Okay. So here we have the pressure will be, will it change? So what we need to do, again, we have ideal gas. So this means we have PV equal nRT. So this means we have pressure is nRT over V. This pressure we will substitute in the equation. So we will have work of expansion contraction. This will be negative integration from initial volume to final volume nRT over V dV. N is constant, 2 moles, 2 moles. Temperature is constant, 300, 300. Or this is the ideal gas constant. So this one will be negative N RT integration from V1 to V2 dV over V. Integration of dV over V, so this one will be negative N RT then V2 over V1, or if you put the negative inside, this will be N RT then V1 over V2. Okay. So from previous example, again, we calculated these volumes. We have V1 is 0.01 meter cube and V2 is 0.05 meter cube, and we have the given here number of moles. This is 2 moles. We have R 8.314 joule per mole Kelvin. Temperature is constant, 300 Kelvin. So this is all the numbers we have. Then substitute in the equation, and you will see in this time work of expansion contraction. This is negative 8028.5 joule, and Q, the amount of heat we have is 8028.5 joule, and this is what we need to find. So the amount of work, the amount of heat will be different based on the process is reversible or irreversible. Clear? See you next lecture.